to get the camera turned back on. And Rebecca is from the University of Toronto and also the Planetary Science Institute. We've asked her to give an invited talk in the dust regolith section. So we are going to, there she is, we see Rebecca, hi, and she's going to talk to us about properties, processes, and significance. Thanks very much. Take it away.
All right, thank you, everybody. Can you hear me?
Yes, we can. Okay. You sound great.
All right, so as Yvonne just mentioned, I've been asked to give a little bit of an overview of some of the talks that will be coming up in session B today, which deal with dust and the regolith. And I will spend a few minutes introducing those talks, and then I'm going to talk a little bit more about some of the stuff that those of us listed here on the screen have been doing with regard to regolith processes. Let's see. Okay. So none of these items of importance of the regolith will come as much of a surprise to this audience, but just in case any of them are, just to make sure we're all on the same page, here are 3 reasons why the lunar regolith is important. First of all, it completely moderates everything that we observe about the moon, because when we look at the moon, what we see is the regolith. And so really it's very important for us to understand how the regolith moderates our observations of the moon if we're going to interpret what's under the regolith. Additionally, it forms the interface between space and the solid moon, and therefore everything that hits the moon hits the regolith. And so the regolith contains a record of the macroscopic and the microscopic bombardment by things like cosmic rays and materials from the sun, and also from meteorites. And so in order to understand those processes, we really have to understand how they've affected the regolith. And finally, as we'll hear quite a few talks about in session B, it includes dust. And there's, as Rick Elphick alluded to earlier in his talk about LADI, there's quite a bit of interest in dust and how it affects the tenuous lunar atmosphere and whether or not it moves around as a function of changes in electrical fields. These things may pose significant challenges to future exploration, and so it's important for us to understand those things as well. In this session, there are a few questions that will be addressed. And so one of the overarching questions about the regolith at the current time is how various species are implanted in the regolith by solar processes, or how they're generated by those processes. And so Micah Scheibel will be talking about hydrogen implantation in the lunar soil, so look out for that talk in session B. Another question is, as I just alluded to, what about the dust? How does it respond to transient electric fields, and what can it tell us about the electrical environment of the moon, and what is it going to do for future landed missions? And there are 3 talks in session B, so I invite you to come and listen to those. Another question is a little bit surprising in the sense that though we have core samples from Apollo and we have other samples of the lunar regolith, there are still many open questions about the fundamental physical properties of the regolith. And so Elise Runts will be talking about some of those physical properties in her talk about the transfer of heat between lava flows and the regolith. And finally, the thing that has concerned me personally for the past several years and really has formed the basis for my work on the Diviner team is this broad question: what is the regolith overturn process? And in particular, I'm interested in the role of rocks and their contribution to the ways in which the regolith is created and buried and re-exposed by the action of impactors. So for the remainder of my time, I'll talk about some of the things that we've been doing on the Diviner team to try to answer this question. And so our approach to this, as Dave Page alluded to a bit earlier in his Diviner overview talk, is to look at the properties of impact ejecta. On this slide, I've shown 3 different radar views of a crater called Kaiser C, which is a relatively small crater on the near side. And in these 3 different radar data sets, in the colors, you can clearly see that the circular polarization ratio shows a signature of abundant blocks, both in the surface, well, either or both on the surface and in the subsurface, associated with the ejecta from this crater. But from the radar data sets alone, we can't distinguish between blocks that are on the surface and blocks that are in the subsurface. And so if we want to understand how blocks contribute to the regolith and the processes forming and altering the regolith, we need to separate those two components. Enter Diviner. Diviner gives us the ability to do this. And so, again, as Dave mentioned, from the multispectral thermal observations that Diviner provides, Josh Banfield has solved independently for the number of rocks on the lunar surface and the temperature of the remaining fraction, which we assume is completely regolith, rock-free. So in the top map here is Josh's older map. There's actually a much nicer map now available on the PDF of the rock abundance. This map is scaled from 0 to 5%, and you can see how the rock abundance picks out the Mare regions very clearly. And then in the bottom panel is the other component, the Regulus Temperature. And so I'll address what we do with each of those separately. So here in the top picture is a very nice depiction of a mixture of rocks and regolith finds, rock-free regolith. In the bottom is a close-up view that shows a rock that Diviner clearly identifies as a rock. This rock is large enough to remain warm throughout the lunar night, and therefore its thermal signature is that of an indurated high thermal inertia material. Whereas the small rocks that are down in the foreground don't show up in Josh's rock abundance map, but they will show up as influencing the temperature of the rock-free regolith fraction. So to exploit these, first we look at the rock abundance data set. So going back to that crater Kaiser C that I showed the radar images for, here's a rock abundance map of Kaiser C. Let me get my little arrow here. Let's see. There we go. So here's Kaiser C. And we see that there isn't anything on the surface that Diviner sees as a rock abundance signature that would correspond to those high circular polarization ratio pixels that I showed in the radar maps. And here's, down on the left-hand side, is a NAC image of a portion of the Kaiser C rim. So you can see that there just aren't any rocks on the surface. If you look around Kaiser C here, you see that from most lunar craters, this is the case. There just aren't very many rocks on the surface. So if it's the case that most craters show very low surface rock abundance, then the implication is that the large ejecta blocks that we know are present, that we see in the radar, must be buried, so that the large ejecta blocks that are on the surface are very quickly removed. So I've started to ask the question, how fast does that happen? And the reason this is important is because it gives us a constraint and an insight into the micrometeorite bombardment processes that actually remove those rocks. So if we look a little bit at some craters of different ages, Dave showed part of this image as well from this paper by Josh Banfield and some of the rest of us on the Diviner team. You can see that, perhaps not surprisingly, the surface rock abundance decreases dramatically with increasing crater age. So up in the left-hand side here is Tycho, and we go down to Menelaus, and we see that there's a very marked decrease in the rock abundance for older craters. And if we quantify that a little bit by looking at some craters with known ages, we see that there's actually a very nice relationship between the number of rocks on the surface and the age of these craters. And in fact, it's a power law relationship with time, the age of the crater in millions of years. So this is a new empirical constraint on the rate at which these ejecta blocks are broken down, at least to sizes that are small enough that Diviner doesn't see them as rocks anymore, which is round numbers about 1 meter in diameter. So this is our first important result. Now separately, if we want to treat the small craters or small rocks on the surface and perhaps larger buried rocks that are buried, say, within a few centimeters to maybe 1 meter of the surface, we can turn to the other quantity derived from the Diviner nighttime temperatures, which is the Regulus temperatures. We've been able to, through the work of Ashwin Basavada and Paul Hain, constrain the density profile of the Regulus fairly well to be an exponential function, as is shown here in the equation, with three free parameters. We've got the bulk density, which is rho sub 0, which is constrained by Apollo core data and other observations. and the surface density rho sub s, which is constrained very well by some of Paul Haynes' eclipse measurements from Diviner. And we're left with the last free parameter being sort of the scale height, if you will, of this density change. So it's the length scale over which the density changes from a very low surface density to its bulk value at centimeter depth. And it turns out that in order to match the nighttime cooling behavior of the regolith, which we can see in the flat portion of the curve on the right-hand side, that slope, the slope of that curve, is a very strong function of h if we take as constrained these other two parameters. So what can we do with that? Well, for one thing, we can make maps, as for instance in this lower panel here. This is a Kepler crater, and we can see that the rock-free portion of the regolith that's in the ejecta blanket shows smaller h values, meaning a shallower depth at which the bulk density is reached near the crater than outside the crater. And that's not surprising. We know there are buried rocks in the ejecta blanket, and there are probably small rocks on the surface. So this is a quantification of that small rock or buried rock population. So the data that's shown in the white box here are plotted in the middle panel of this plot against curves generated by these standard 1D thermal models that Dave Page alluded to earlier, with different h values plotted. So if I didn't include for this talk, but if I had showed a plot of the same craters that I showed in the rock abundance plot, the best fit average h values for these ejecta blankets as a function of age, it would look just like the rock abundance plot that I showed earlier. So what that says is that the large surface rocks and the small and buried surface rocks are breaking down at the same rate. So this has enabled us then to gain new insight into the time dependence of the rate at which these rocks are breaking down to form regolith. Specifically, if we just look again at this power law function of time, and we investigate, what that means, we see that after only 100 million years, we're down to 34% of the initial rock population, and 76% of the total loss that occurs at 1.7 billion years, which is the end of our signal, has occurred by 100 million years. And that rate then tails off as the craters get older. And the reason for that is because we're losing blocks, and the remaining blocks are being covered by the newly produced regolith. So again, this indicates an extremely rapid transition from a rocky thermophysical signature of the ejecta blankets to a dusty thermophysical signature. And this implies that initially at first we're experiencing an extremely fast buildup of regolith. So as I said a moment ago, the importance of this result is that though in the past we've had estimates based on probabilistic models of cratering average rates for regolith buildup and for rock destruction, we now have for the first time an empirical estimate of the time dependence of that rate and how that rate changes through time. And so what we hope to do with that, or what is possible to do with that then, is to use this result as input for models of regolith overturn, and something that Paul Lucy on the Diviner team is very interested in is plugging these results into models for space weathering. So a very important issue when you're trying to understand how space weathering occurs in the picture of regolith overturn is understanding how fast new unweathered material is generated and how that should be incorporated into the models. So that's a summary of what we've been doing with regard to regolith evolution. You haven't said that I only have 2 minutes left, so maybe I talked fast, but I think that's all I have for now. So.
Well, you're right on time. I was just about to tell you 2 minutes.
Okay.
Okay, thank you so much, Rebecca. Excellent talk, just absolutely fascinating to me too. I think that Rick has already typed in a question for you, and he says, what do you think this rapid disruption means for ancient polar ice deposits, if originally massive?
It's a good question, Rick. I haven't thought about this. I think that's a very good question. I think what it implies is that if there were massive polarized deposits and they weren't buried very deeply, then they wouldn't last very long. So if there are massive polarized deposits, then they must be buried under, say, 20 or more centimeters of regolith. What we found is that, thermophysically speaking, we can't really tell the difference between a large rock, even a sheet of bedrock that's buried under more than 20 centimeters of regolith, and one that's buried under a meter. So I think that gives us a little bit of a constraint on how deeply those things must have been buried if they're still present.
Wow, excellent. Really neat. Let's see, we have someone else typing right now. I believe it's Rama. Oh, Carly. Carly, but I don't see the question yet. Okay, here it comes. From Carly. Does thermal recycling play a role in addition to impacts? I guess that would suggest a latitude effect.
Thermal recycling. I don't know whether you can respond to this, Carly, but do you mean the effects of thermal cycling and its effects on the breakdown of rocks? If that is what you mean, then I'll point out that Marco Delbo has been doing some work on that very issue. And yeah, I think that for sure. Okay, she says yes. Yes, I think that must play a role, and that, clearly that would be a contributing factor to the results that we see here. So if you're really interested in that process, talk to Marco.
Mm-hmm. Okay, great. And we're just out of time, but let's take this last one. It says, from Rama, it says, could you please elaborate on the relation between temperature and the age of the craters?
Okay, I'm not really sure what you mean by to elaborate on that relationship. Maybe we should talk offline and I could explain a little bit more clearly what it is that we do in the modeling, and maybe that would answer the question.
That's a great idea. So please do that. Take it off into the chat room, and we are now going to move into our next round of lightning round talks. But thank you.